But of course there are many reasons why we want to find out a way to quantify bandwidth in a reasonable way. And the biggest reason is because it's really relative bandwidths that are important. We intuitively know that if we have a signal that's very wide in bandwidth, like let's look at the lower, the B case here, where X of F is the spectrum of the input signal, and it's very, very wide, and we look on the right in the B case, and we have a channel that's fairly narrow. Well, we know something's going to go terribly wrong when we try to put this input signal through that narrowband channel. If we're in the upper case, in part A at the top, where the input spectrum is fairly narrow relative to the response of the channel, we think that our signal is going to get through without much distortion. So we know this intuitively. We look at it by eye, but we really need a way to quantify each of these signals, which each of the channels, each of the signals has infinite bandwidth if we go by a strict definition. But of course, practically there's some finite bandwidth we can use. So there's several definitions for bandwidth that are available. I'm going to focus just on two of them that we see the most often, which is the 3 dB or half power bandwidth and the noise equivalent bandwidth. I think I also use null to null in some of my examples. But in any case, very simple definitions. The 3 dB bandwidth, also known as the full width half maximum bandwidth. We take the frequency response, we look at the peak of the peak frequency response, and then we follow the frequency response down to where it first reaches half of the initial value. At that point, we look down at what bandwidth has occurred, and we call that the bandwidth of the signal. So this is the 3 dB bandwidth of the signal. Now a second definition, and one that we need when we're modeling noise, is noise effects, is something called the noise equivalent bandwidth. So in this case, on the left in blue, we have an arbitrary, I think this is obviously a sinc function, but just say an arbitrary frequency response with infinite frequency support. If we take the area under the curve, and then, we can do this numerically if we have to. We can do it analytically if we have a good expression for it. But the important thing is that we form afterwards a rectangle with the same height as the maximum of the original frequency response. So the original frequency response has a maximum of A, so we fix our rectangular frequency response to a height of A, and we define the bandwidth B to be that bandwidth that has equal area, gives equal area to the rectangular response that we would get under the area of the curve and the original response. Okay, so that's one definition of bandwidth. And why do we call it the noise equivalent bandwidth? That's because we assume that we're dealing with additive white Gaussian noise, which is flat in the spectral domain and has infinite frequency support. So suppose we took this additive white Gaussian noise signal and we filtered it with the frequency response in blue. Well, then the power of the noise that would be emitted would be the equivalent as if we had used a rectangular filter with bandwidth B, well, two small b's here. That would be the noise power that was let in by this filter. So if we want to simply know what is the effect of a wideband additive white Gaussian noise being filtered by this filter, we could say it's the same as if we had used a rectangular filter. As far as the noise is concerned, this could simplify our analysis, but of course the signal, perhaps the effects will be different. But as a way of characterizing a filter, this is a very useful characterization of bandwidth. So here's a graphic for the sinc squared function, and this shows how different the results are for what we would call the bandwidth of this signal, just based on definition. So different definitions give different values for bandwidth. It's important simply to understand when you read what the bandwidth is, what it's referring to, and how it may be useful to use. 3 dB bandwidth may be a good figure of merit for determining how much distortion will be introduced to a signal. The noise equivalent bandwidth will be a good tool for determining how much noise is getting into your system. If we move on just on this brief review of filters, one other concept which is very important is the causality effect. A definition of a causal filter. A causal filter is a filter whose output is only a function of prior inputs. That is, the output is not a function of the future. That means we cannot build a system that predicts the future. Of course, all practical filters are causal filters. However, in the mathematical domain, we will often play with, design, exploit, take advantage of non-causal filters. But you have to always keep in mind that when it's time to build these filters, that there's some accommodation has to be made to make them into practical filters. And then again, just to see the impact of what a causal filter is, let's look at the impulse response, small h of t, of a system. We have the output y of t is equal to the convolution of the impulse response h with the input signal x. We have the integral definition of a convolution. And then finally, to the right, we have changed the limits of the integration from minus infinity to infinity to instead be from minus infinity to t, the current time. So the output y of t can only be a function of the signal x of u here inside of the integration from the negative infinite time until the present point. That means that we have assumed that h of t, the impulse response, is 0 for all negative values of the argument. Causal filter is a filter whose values are 0 for negative values of the argument. For instance, let's look at the low-pass filter. If we look at what is a causal version of a low-pass filter, not an ideal low-pass filter, but a filter that filters out high-frequency content. Well, one version would be an RC. This is a resistance capacitive circuit, an RC circuit, that forms a low-pass filter. And we can see that it has a frequency response that is 0 and then falls off exponentially. If we look at the frequency response for our ideal low-pass filter, it's the sinc function, and of course it has infinite time support. So this is a non-causal filter. Of course, the more high-frequency terms are introduced with the causal RC realization, and we would like to get something that approaches the ideal filter, cutting off more high-frequency components, if we could get an approximation to the ideal low-pass filter. So what we can do is to render the ideal low-pass filter causal. And in order to render the filter to be causal so that we can actually build it in the lab, is to first truncate the impulse response so that it is no longer infinite. And then we have to introduce a delay. There's a trade-off between how sharp is the cutoff in the low-pass filter in the frequency domain, depending on how much we truncate it. So if we let it go farther and farther, the impulse response wider in the time domain, of course we'll get a sharper cutoff in the frequency domain, but that will mean that we have to introduce more delay before we can take the output and use it. So there's a trade-off. But anyway, this is just to say that although ideal filters don't exist in reality, there are ways that we can approximately achieve it.